In Part 3, last part of introduction session, we dive deeper into the using formulas to get you ready for the engineering approach in this course. We'll kick things off with a quantitative example of air pollution caused by a power plant. Let's break it down step by step. This slide demonstrates that power plants are significant sources of primary pollutants, focusing on the emissions generated from using different types of coal. Here, I present the specific emission values from power plants fueled by various coal types, highlighting the environmental impact of each. Let's look for the source and cause of pollutants. NOx, illustrated as being produced from air, specifically nitrogen N2 and oxygen O2, when subjected to high temperatures, around 1600 degrees C or 2900 Fahrenheit, as seen in combustion engines. It is important to emphasize that the presence of nitrogen and oxygen from air produces NOx. The use of sulfur-containant fuels in heavy diesel engines, such as those in ships, produces SO2. Standard automobiles also contribute to pollution, especially NOx, due to the high-temperature combustion of fuel in car engines and the presence of nitrogen from the air entering the reaction zone. To reduce NOx emissions, the installation of catalytic converters is mandatory, as they remove almost all NOx from car exhaust. SOx, sulfur oxides, and particulate matter, both are primarily emitted from the burning of fossil fuels. Carbon monoxide arises from the partial oxidation of fuels. Emission data by fuel type. This part of the slide details the emission levels of various pollutants per gigajoule, GJ, of energy produced from different types of coal and oil, as well as from gas. CO2, SO2, NOx, CO, and particulate matter. The table lists specific emissions for hard coal, brown coal, fuel oil, other oil types, and gas. It highlights, for example, that brown coal has higher emissions of CO2 and SO2 compared to other fuels. The slide is designed to educate on the environmental impact of different energy sources, illustrating how various fuels contribute to air pollution through their specific emissions of major pollutants. This knowledge is essential for understanding environmental impacts and for shaping policies or technologies aimed at reducing emissions. This example demonstrates how to estimate the pollutant output from a power plant using coal as its primary energy source. The Big Bend Power Plant, located in Tampa, Florida, converts heat from coal combustion to electricity with a 33% efficiency rate, producing 1.73 gigawatts of power. The image and table provided below depict the power plant and list the amount of pollutants generated in grams per gigajoule of energy produced by burning coal. These figures are crucial for calculating the annual pollutant production. To determine the power required to generate 1.73 gigawatts, or gigajoules per second, we use the plant's efficiency. I have laid out the units clearly to simplify the calculation. Remember to cancel out the units step by step to arrive at the correct unit for the final result. When converting power to energy, we multiply the result by the number of seconds in a year, assuming that the power plant operates non-stop 24/7. Keep in mind, this is an ideal scenario, and actual operating times may vary. From these calculations, we derive the total energy required to run the power plant for a year by burning coal. To calculate the annual pollutant output, we multiply the energy produced by the emission factors from the table. The results, expressed in grams, are then converted to metric tons unit. This power plant produces approximately 15.6 megatons of carbon dioxide, 126 kilotons of sulfur dioxide, 14.8 kilotons of nitrogen oxides, 14.7 kilotons of carbon monoxide, and nearly 199 kilotons of particulate matter annually. It's evident that installing air pollution control equipment is necessary for the power plant to comply with air quality standards. This case highlights the importance of our course in addressing such environmental challenges. You will learn how to select the appropriate size and type of equipment needed to control emissions effectively and meet national standards. Just a friendly reminder that understanding how to use the ideal gas law in various situations is crucial. Familiarizing yourself with the ideal gas formula now will pave the way for grasping more complex calculations later. Let's start with a simple exercise. calculating the density of air in kilograms per cubic meter at 2 atmospheres and 50 degrees Celsius. The ideal gas law states that the product of pressure as P and the volume of gas as V equals the product of the number of moles as N, the gas constant as R, and the temperature as T. You can find the gas constant in various units in the table below. By rearranging the equation, you can determine the total concentration, C, of the gas. To convert this to total density as ρ, multiply the concentration by the molecular weight of the gas as mW. I'll demonstrate how to calculate the density using the ideal gas law, highlighted in red. Remember, the molecular weight of air is approximately 29 grams per mole. For our calculation, we use a pressure of 2 atmospheres and a molecular weight of 29 grams per mole. It's important to note that the temperature must be in Kelvin or Rankine. For this case, we'll use Kelvin by adding 273 to the Celsius temperature. I'll display the units for each parameter to help identify the appropriate gas constant as R. The final calculation shows that the density of air as an ideal gas is approximately 2188 grams per cubic meter. By applying a conversion factor, we find the result to be about 2.188 kilograms per cubic meter. Every country sets its own air quality standards to regulate pollutant levels. If you are viewing this video from outside Canada, the chart displayed may still provide useful reference points for understanding pollutant concentration levels. For specific guidelines applicable to your location, please consult the air quality standards in your own country. This will give you a more accurate understanding of local environmental regulations and their practical implications. This chart presents the Canadian National Ambient Air Quality Standards, showing the evolution of numerical values for different air pollutants across 3 specific years: 2015, 2020, and 2025. Here's a breakdown of the information in the chart. Pollutants covered: fine particulate matter, PM2.5, ozone, O3, nitrogen dioxide, NO2, sulfur dioxide, SO2. Averaging time: each pollutant has standards based on different averaging times to address how long the pollutant's concentration is measured. 24-hour and annual for PM2.5, 8-hour for ozone, 1 hour and annual for nitrogen dioxide, 1 hour and annual for sulfur dioxide. Standards over time. For each pollutant, an averaging period, the chart lists the standard numerical values in parts per billion, ppb, or micrograms per cubic meter, showing a general trend of more stringent standards over time. For example, PM2.5 annual standard decreases from 10.0 microgram per meter cube in 2015 to 8.8 microgram per meter cube in 2020, and further to 8.0 microgram per meter cube by 2025. Ozone standards decreased from 63 ppb in 2015 to 60 ppb by 2025 for the 8-hour average. For newly regulated pollutants like nitrogen dioxide and sulfur dioxide in 2020 and 2025, the standards are introduced and then tightened. These standards are set to protect public health and the environment from the harmful effects of air pollution. Over the years, as shown in the chart, standards become stricter to likely reflect new scientific findings about the health impacts of pollutants and technological advancements in pollution control. This chart is a useful tool for tracking regulatory progress and understanding how air quality standards are planned to improve over time, helping policymakers, researchers, and the public measure environmental health progress. In this example, we'll explore the concept of concentration units for a species in a mixed gas. Assume we want to determine the concentration of carbon monoxide in the air at 170 degrees Celsius in 2 atmospheres, expressed in micrograms per meter cube of mixed gas. The desired level of carbon monoxide for a 1-minute-hour period is 13 parts per ppm. Firstly, it's important to understand that ppm, or part per million, is a unit of concentration used in gas phases, referring to parts of a species per million parts of gas. This can be in terms of volume or moles. Therefore, 13 ppm indicates there are 13 moles or volumes of carbon monoxide per million moles or volumes of the gas mixture. Please note that if this measurement refers to pure air, then the volume of CO at 13 ppm would need to be subtracted from the total mixed air to determine the volume of pure air. However, in this scenario, our calculations are based on a mixed gas. Another critical detail is the standard condition under which the 13 ppm is reported, typically at 1 atmosphere and 25 degrees Celsius. To proceed with the calculations, we begin by determining the number of moles of carbon monoxide corresponding to a volume of 13 cubic meters at 25 degrees Celsius and 1 atmosphere. Interestingly, this value remains constant, regardless of changes in gas conditions. Applying the ideal gas law, we use 1 atmosphere for pressure and add 273 to 25 degrees Celsius to convert the temperature to Kelvin. The appropriate gas constant is 8.205 by 10 to the power of minus 5 atmosphere cubic meters per gram mole Kelvin. The resulting calculation shows 531.7 gram moles of carbon monoxide. The problem also asks for the weight of carbon monoxide in the mixture. By using the molecular weight of CO 28 grams per mole, as CO consists of carbon 12 and oxygen 16, and converting from grams to micrograms, the total mass of CO in micrograms turns out to be approximately 1.489 by 10 to the power of 10. Finally, it's crucial to adjust the volume of 1 million cubic meters of mixed gas to the new operating conditions of 2 atmosphere and 170 degrees Celsius. For this, employing the ideal gas law twice, once for each set of conditions, helps us find the adjusted volume of the mixed gas at the new conditions, which is approximately 743,289 cubic meters. Dividing the total mass of carbon monoxide by the adjusted volume gives us the concentration of CO in micrograms per cubic meter, which calculates to about 20,033 micrograms per meter cube. In this frame, I present another calculation scenario. For this case, the problem statement asks us to determine the concentration of carbon monoxide in pure air under new conditions. Please take a moment to pause the presentation and try this calculation on your own. Once you're ready, resume the presentation to compare your results with mine. In an environment free from particulate matter, visibility would be perfectly clear. As the concentration of particulate matter increases, visibility decreases significantly. This happens because particulate matter scatters light, causing objects in the distance to appear blurred and dimmed, much like the experience during a foggy day, where objects seem hazy and less distinct. This scattering effect substantially reduces the contrast and clarity of distant objects, essentially acting as a filter that dims and blurs the visuals. The provided animation helps visualize this concept by showing a viewer observing 2 objects, a plain green square and a vibrant flower, set against a green backdrop. The lines from the objects to the viewer's eye depict the path of light and demonstrate how it is modified by particulate matter in the air. The concepts of apparent and actual contrast can be quantified. Starting with the definition first, apparent contrast, C, is the perceived visibility of an object from a distance, influenced by light scattering due to particulate matter. It naturally diminishes with increasing distance. Actual contrast, C0, is the inherent visibility of the object without any particulate interference, representing the clarity that would be observed in a particle-free environment. Mathematically, the apparent contrast, C, is equal to the product of C0 by E raised to the negative power of sigma by D, where E is the base of natural logarithms, sigma is the extinction coefficient, which quantifies the amount of light absorbed and scattered by airborne particles, and D represents the distance between the observer and the object. Understanding these dynamics underscores the importance of air quality in maintaining visibility. It bridges environmental science and optical physics, providing a clear explanation of how particulate matter affects our daily visual experiences and emphasizing the significance of reducing air pollution to sustain clear and healthy environmental visibility. This narrative ties together the theoretical aspects with practical observations, enhancing the educational value of the movie. The concept is applicable to the absorption of light by NO2. As the concentration of nitrogen dioxide increases, visibility decreases significantly. This happens because NO2 molecules absorb light, causing objects in the distance to appear blurred and dimmed. Mathematically, the apparent contrast C is equal to the product of C0 by E raised to the negative power of sigma NO2 by D, where E is the base of natural logarithms. Sigma sub NO2 is the absorption coefficient of NO2, which quantifies the amount of light absorbed by NO2. Con sub NO2 is concentration of NO2 in the air, and D represents the distance between the observer and the object. Please pay attention that the exponent has no unit. Practicing the equation, when apparent contrast is 0.2 times of actual contrast, distance can be calculated based on the scattering extinction coefficient. Further analysis determines the limit of visibility, which is the farthest distance at which an object or light source can be clearly seen or recognized by an observer. This metric is crucial in fields like meteorology, navigation, and aviation, where visibility directly impacts safety and operational decisions. Factors that affect the limit of visibility include lighting conditions, any obstacles present, atmospheric conditions such as fog, rain, or pollution, and the observer's natural visual capabilities. Essentially, it quantifies how far one can see before details are obscured by environmental influences or human visual limits. In City X, the concentration of particulate matter is 150 microgram per cubic meter. Given the optical properties of the particles with a value of A equal to minus 0.02 per kilometer and B equal to 0.03 cubic meters per kilometer per microgram, we can calculate the limit of visibility in kilometer. First, we calculate the extinction coefficient using A, B, and the concentration of particulate matters. With the provided values, the calculated sigma extinction coefficient is 0.43 per kilometer. Applying this value to the visibility equation derived from the previous discussion, the calculated visibility limit D is approximately 9.1 kilometers. This means objects beyond 9.1 kilometers are not visible under the current atmospheric conditions. If particulate matter, NOx, and other chemicals are present, the overall apparent contrast is significantly reduced. This can be explained by the total extinction coefficient, which is a linear combination of the individual extinction coefficients. The total extinction coefficient equals the product of the NOx absorption extinction coefficient and the NOx concentration in the air, plus the extinction coefficients of particulate matter and other chemicals. The apparent contrast can thus be expressed by the total extinction coefficient. The Air Quality Health Index, AQHI, is a tool used to communicate the quality of the air in a way that is easy to understand. It helps individuals know how clean or polluted the air is and the associated health risks. The AQHI is particularly useful because it considers the combined effects of multiple pollutants known to harm human health, rather than measuring them separately. Below shows the chemical and fine particles are included in the AQHI calculation: nitrogen dioxide, NO2, sulfur oxides, SOx, carbon monoxide, CO, ozone, O3, at ground level, and particulate matter, PM 2.5, and PM10. Air Quality Health Index, AQHI, in Canada. The Air Quality Health Index, or AQHI, is a scale designed to help you understand what the air quality around you means to your health. The AQHI is calculated based on the relative risks of a combination of common air pollutants which are known to harm human health. These pollutants include ozone at ground level, particulate matter PM 2.5 and PM10, and nitrogen dioxide. It is a health protection tool that is designed to help you make decisions to protect your health by limiting short-term exposure to air pollution and adjusting your activity levels during increased levels of air pollution. It also provides advice on how you can improve the quality of the air you breathe. This index pays particular attention to people who are sensitive to air pollution and provides them with advice on how to protect their health during air quality levels associated with low, moderate, high, and very high health risks. It measures the air quality in relation to your health on a scale from 1 to 10. The higher the number, the greater the health risk associated with the air quality. When the amount of air pollution is very high, the number will be reported as 10 plus. The AQHI is measured on a scale ranging from 1 to 10 plus. The AQHI index values are also grouped into health risk categories as shown below. These categories help you to easily and quickly identify your level of risk, 1 to 3 as low health risk, 4 to 6 as moderate health risk, 7 to 10 as high health risk, and 10 plus as very high health risk. Health messages customized to each category for both the general population and the at-risk population. The AQHI is designed to give you this information in one place, along with some suggestions on how you might adjust your activity levels depending on your individual health risk from air pollution. The U.S. Air Quality Index, AQI, is the EPA's tool for communicating outdoor air quality and its implications for health. The AQI features 6 color-coded categories, each corresponding to different index values. Higher AQI values indicate increased air pollution and greater health risks. For instance, an AQI value of 50 or below signifies good air quality, while values over 300 indicate hazardous conditions. An AQI value of 100 generally matches the ambient air concentration equal to the short-term national ambient air quality standards, aimed at protecting public health. Values at or below 100 are considered satisfactory. However, when AQI values exceed 100, air quality is deemed unhealthy, initially for sensitive groups, and then for the general population as the values rise. The AQI is segmented into 6 categories, each associated with a specific level of health concern and represented by a unique color. This color coding system allows individuals to easily assess air quality and potential health risks in their area. Aquicon.org is an informative website that offers detailed air quality data for various cities and regions across more than 100 countries. The website uses the Air Quality Index (AQI) scale defined by the U.S. Environmental Protection Agency (US EPA) based on the 2016 standard. This scale ranges from 0 to 500, with higher values indicating worse air quality and greater health impact. The site includes maps and comprehensive information about pollutants, providing insights into air quality levels worldwide. The first map displayed on the site shows the Air Quality Index for Ontario, Canada. To view the Air Quality Index for your region, please visit the website and use the URL provided. If you are interested in specific city data, you can refine your search by including the city name in the URL, as demonstrated on the site. However, my favorite website, where you can find beautiful and valuable information, is Ventusky, or the Ventusky website. You can easily search for it on Google and find the Ventusky website. The user interface is very nice, professional, and provides a lot of information at the same time. When you visit the website, it shows the temperature in the area you click on. Currently, I live in North America, and you can see how the temperature is quite severe. For instance, at 9 o'clock on January 20th, 2025, the area where I live is showing a temperature of minus 38 degrees Celsius. Near the lake it's minus 31 degrees, and in New York City, it's minus 8 degrees. One beautiful feature is the menu on the right-hand side, where you can click on the camera icon to access available online cameras in different regions. In addition, you can switch the temperature display between Celsius and Fahrenheit. You can even click on the calendar to select a specific day. If you want to observe weather patterns, just play the animation and you can see how the temperature changes hourly over the next 14 days. For our course, the focus is on air quality. If you go to the menu on the left-hand side, you'll find valuable information about humidity, wind gusts, wind speed, and at the bottom, air quality. This is our primary focus. When you click on air quality, it displays data based on specific values. For instance, on the right side you'll see measurements in micrograms per cubic meter. If you check the menu, under air quality, you'll find PM 2.5, which refers to particulate matter smaller than 2.5 micrometers. In my area, PM 2.5 is currently 0. Interestingly, there is a natural fire in California, and in some places like Bakersfield, PM 2.5 levels are 22 micrograms per cubic meter. You can also explore other pollutants using the left menu. For example, you can check the levels of SO2. Currently, SO2 is almost 0. However, NO2 levels around the Los Angeles area are high due to heavy traffic. One great feature is the ability to hover over any country. For instance, if you look at China, you can see that NO2 levels are extremely high, reflecting significant traffic and industrial activity. When you switch to the air quality index, you'll see specific locations, such as Suzhou, where the air quality index is 400, which is extremely unhealthy. This website provides excellent information on air pollution and air quality worldwide. It even predicts future conditions based on wind streams. I hope you find this information helpful and enjoy exploring it. The Introduction to Air Pollution offers a comprehensive overview of key topics essential for understanding air pollution dynamics. This session covers air criterion pollutants. Students learned about the major pollutants regulated under air quality standards, including their sources and the detrimental health effects they can cause. Sources, causes, and effects. This section delved into the origins of air pollutants, the processes through which they are emitted, and their environmental and health impacts. Using the ideal gas formula for different calculations, the examples showed how apply the ideal gas law to calculate various air quality parameters, enhancing their ability to analyze and interpret air pollution data. Visibility. The course explored how pollutants affect visibility, discussing the mechanisms through which particulates and gases obscure visibility, and how this serves as an indicator of air quality. Air Quality Index calculation. Students explored the significance of the Air Quality Index, AQI, a metric that communicates daily air quality and its potential health impacts. Great job so far in this air pollution control course. If you found this session helpful, leave a comment and subscribe for more. Don't miss next session, where we'll dive into process flow diagram and mass balance. It's gonna be exciting.